So remember, we've been talking about sampling distributions, how they relate to a population distribution. We've been given information about the population, and then we've been able to find information about the sampling distribution and use it to solve some problems. Now, that's not normally the way it works. Normally, the way it works is we don't know about the population. That's what we're trying to answer questions about. So we use the sampling distributions and then make calculations about the population. That's going to be the rest of the course after we finish this, but it's important to know the relationship between population distributions and sampling distributions. And so far we've talked about proportions, and that's one big area where we solve problems in statistics, claims about certain proportions. You know, things like 4 out of 5 dentists prefer this brand of toothpaste. I mean, how valid is that claim, right? So that would be an example involving proportions. However, many other questions involve means, the average of something. So let's say there's a claim that the average something is this amount. We want to know if that's actually true, okay? Or whether it's less than that amount, or whether it's possibly greater than that amount. So we're going to change our thinking from proportions to means, but everything else is pretty much the same. The conditions are just a little bit different, okay? But it's really going to be very similar to what we did in 6.2 and 6.3. Like I said, instead of proportions, it's going to be means. So the problem we're going to look at, in 2014, Veterans Affairs Health System. So that's a health system for people that have been in the armed forces. They came under fire for having long wait times. Many veterans couldn't get appointments for months, especially mental health ones. These delays can be high stakes. Because if you look here, it says, according to the VA's latest report, the U.S. now have just 17 veteran suicides per day, often linked to PTSD and depression. So they changed the leadership of the Veterans Affairs, and they vowed to speed up wait times. And they actually vowed to say, okay, we're going to actually meet a reported 3-day wait time average. So the average wait time is they want to be 3 days, standard deviation of 1 day for mental health appointments specifically. Okay, so we know something about the population, what the claim is. They want an average of 3 days with a standard deviation of 1 day. But does that actually happen? So the information we are given is mu, which represents the population. So we are given that, it's 3. We are actually given the population standard deviation, it's 1, okay? But in order to test to see if this 3-day wait time with 1 day standard deviation is working, we need to take a sample. And then we need to study that sample by taking repeated samples and seeing what happens. So we are going to take a sample mean, which the notation changes to X bar. So that's the sample mean. Remember, a population measure is called a parameter. A sample measure is called a statistic, and we use this as a measure of this. So what was done to check this 3-day claim? There was a random sample taken from 4 VA clinics, and or sorry, that was something else. That was another activity that we just don't have time to do. The sample was taken of 30 clinics, a random sample. And sample mean wait time when that random sample was taken was 5.33 days, which suggests right away that maybe they aren't meeting the 3-day wait time because it's over by a couple of days. But we just don't know for sure. Okay. So the population in this situation is the true mean wait time. For all clinics. Whereas the sample we took, its measure is the sample mean of 30 clinics. Remember, the parameter for the true mean, the actual mean of the population, is called mu. Okay. And the stated goal, what we're going to base on, is 3 days. But when we took a sample and found the average, we found X bar, the sample mean, and that turned out to be 5.33 days. Where? Where did that come from? Hey, whoa. Oh my, okay, I'm just gonna leave it. Okay, stop. Stop. Okay, I'm not gonna touch it. All right. So what are things going to look like? Well, we're going to have our population distribution, and it's going to average out to 3 days. That's what the goal is. So we want it to look something like this. Maybe it's going to be slightly skewed to the right. Maybe it's going to be normal. Okay. Maybe it's going to be slightly skewed to the left. When we actually took a sample of 30 clinics, it looked like this. Okay. So fairly spread out, kind of centered around 3 days. Okay. But if we did this 30 clinic sample numerous times, it's going to look like this. It's going to approach normality, and it's going to be a little tighter towards the mean. Okay. So that's what we're sort of going to expect to see. Now with the sampling distribution, remember, we want to see, is this 5.33 unusual, or did we just sort of get it by chance? Okay. In order to do that, we've got to find the mean of the sample means, and we've got to find the standard deviation of the sample means, and we got to make sure it's normal. So it's going to look like this, the sampling distribution. If we meet the conditions that it's normal, which we'll talk about in a second, and if we meet the other two conditions, which we'll also talk about in a second, the average of all those sample means we took of 30, size 30, because it's a good estimator of the population, we can say that it equals the population mean. Okay. Sample mean is a good estimator of population mean, just like sample proportions are a good estimator of population proportion. And to find the standard deviation, we're going to use this formula, which you will always get. It's going to be the population standard deviation divided by the square root of the sample size. So it's a slightly different formula when we're dealing with means. Remember, with proportion, it was the square root of p times 1 minus p divided n. Here, it's a little bit different with means. But again, you'll get those formulas. What's that?
I thought X bar was sample mean, but is it like sample? I mean, that's the mean symbol? Like, why is it mean symbol X bar?
Because remember, in order to test our claim, we're taking a whole bunch of samples and then we're averaging those samples. Yeah, I know it's a little. You're kind of using the same, you're using two different notations in the same thing. I get what you mean. Okay. So in this situation, we can go ahead and calculate the standard deviation. Standard deviation of the sampling distribution, when we take several samples of 30, is going to be the standard deviation of the population. I'll just rewrite this one. Divide the square root of the sample size. So remember, the standard deviation of the population from the previous page was 1 day. The sample size we always took was 30. So 1 over square root 30. And that's going to give us approximately 0.183. What's the interpretation? Sample mean wait times typically vary by 0.183 days from the true mean of 3. You don't have to say 3, you can just say from the true mean. And remember, this is going to be 3. So we've got, this is 3. We've got this as 0.183. We have to check to see if it's normal. And then we can do our calculations using normal CDF to figure out if 5.33 days is unusual or not. So this I sort of talked about earlier. Without doing any calculations, 5.33 days was higher than the goal that they set of 3 days. So yeah, kind of surprising. It's over 2 days there. Okay. Which suggests they haven't met the goal. However, we need to be more sure than just saying kind of. Or seems to suggest they haven't met the goal. More studies needed. We're skeptical right now. But we need to back that up with some proof. And that's where the math comes in. Okay. So remember, so we've done some calculations, but we got to make sure those conditions are met so that it allows us to do those calculations and it allows us to make those statements. And the first two conditions are the exact same as when we did proportions. Where am I now? Oh yeah. So in order for us to say, to use the population mean in our calculations? Okay? Or in our inference. Remember, it has to be a random sample. So if we assume this is the population distribution of the mean weight days, and then we took a whole bunch of samples, we would expect it to look like this. To center around the same as the population mean. Okay? But if we use a voluntary response sample, let's say we said, we sent out a thing saying, send us your average wait times. That makes it voluntary response. That's bias, right? Okay. Chances are we're going to get something like this. Okay. Which is the mean wait days is actually going to be less. Why do you think it would be less?
People have less wait times.
What's that?
People have less wait times on the wait.
Exactly. I mean, if you've got a wait time of 10 days, are you going to respond? Probably not. But if you got a wait time of 1.5 days, yeah, you're probably going to respond. Okay. So with random samples, the average of all the sample means is going to be the same as the average in the population distribution. But if we do a voluntary response, we would expect the average in the samples to be less than the population because only those that have lower wait times will be reporting. So that's the importance of a random sample. Okay? So clinics with long wait times won't share their information. But clinics with short wait times will. That's what we expect to happen. So again, it speaks to the importance of a random sample. And if we go back to the question, okay, we did random sample 30 clinics. This is what would happen if we did it, if we just got a voluntary response. So that allows us to say with a random sample, that allows us to say this. So we can say that the average of all the samples we took is going to be 3, which was the population wait time average. That was the goal. So we can move on from that. Now the standard deviation. Can we use the standard deviation formula? Yes, as long as the 10% condition is met. And remember the 10% condition, the sample size, which in our case is 30, must be less than 10% of the population size. Or in other words, little n, sample size, must be less than 0.10 times capital N, population size. And like I said, it allows us to use this formula. So we'll talk about this when we sort of put the whole problem together towards the end. But one would assume that we've met the 10% condition. Because if we sampled 30 clinics, that means there has to be at least 300 clinics in the US. That's a pretty safe bet. We can reasonably assume that there's more than 300, so we've met that condition. Finally, the normal condition. That allows us to use normal CDF calculations. Okay? This is slightly different. We don't do the sample proportion times n is greater than or equal to 10 and n times 1 minus the sample proportion is greater than or equal to 10. We use something different. It's called a normal or large sample. So one of two things has to happen. You either have to be told that it's normal, in which case you don't have to worry about this condition, if it says in the question that it's normal. Or the sample size you take is greater than or equal to 30. Because what happens is that your sample size is large enough, okay? The distribution will always approach normal, even if the original one isn't. And that's what this sort of explains here, okay? So here we have a population distribution. Then we take a whole bunch of samples and we average them out, but the sample size is only 2. Again, stays normal, fairly spread out. If we increase the sample size, stays normal, a little bit tighter. Because remember, when we increase the sample size, the standard deviation shrinks. The variation is less. If we go even higher, it's even tighter and stays normal. So that's what happens under normal if the original one is normal. But what if the original one is not normal? Like this one is slightly skewed to the left. If we take a whole bunch of samples, but the sample size is only 2, it's going to be pretty similar. Maybe a little less variation. But as we increase the sample size, not only does it get tighter, but it actually gets more normal. So you can see we've got a skew there, a little bit less of a skew there, and now we're approaching normal. So if the sample size is big enough, we can say that it's normal, which allows us to do the normal calculations. So if the original one is normal, doesn't matter what sample size we take, they're going to be normal. But if the original one is not normal, okay, the sampling distribution will only approach normal for larger sample sizes. As in greater than or equal to 30. That seems to be the mark. Yeah.
Is it greater than or equal to 30 for this specific experiment or for any populations?
Any mean question. Yes.
So
And any population size, yes. So that thing, what happens if the original is not normal, but if we increase the sample size, it becomes normal, is actually a certain mathematical theorem called the central limit theorem. Okay? And it basically says when n is big enough, the sampling distribution per sample means will be approximately normal. And why is it so useful? Well, because, yeah, the original shape and that's the population. Doesn't matter. As long as your sample size is big enough, it's going to become normal. The original shape or the original shape of the original distribution. Just trying to shorten the writing. So just to summarize, and this is what we did with population proportions. We can do normal calculations to solve these kind of problems if it's normal. Okay. So the large count conditions allows us to say it's approximately normal, which allows us to use normal CDF. And of course, to use normal CDF, we need to know a mean and a standard deviation. Well, the mean of the sampling distribution is going to be the mean of the population, because this is an unbiased measure of this. So it allows us to state that. And it also allows us to calculate the standard deviation of the sampling distribution by taking the population standard deviation divided by the square root of the sample size. So it gives us a calculable variation or calculable spread. Okay, so pulling this all together in the original problem. Last thing we need to do. So if we're making the assumption that the wait time or the population mean is 3, because that's the claim or the goal that's being, the claim that's being made or the goal that's being stated. Okay, we randomly sampled 30 clinics, found the sample mean wait time. We want to describe the sampling distribution of X and check the conditions. So remember, random, 10%, and normal or large sample. One of the two meets this condition. Well, we already found out with the random, but go back to the original problem, the 30 clinics were randomly selected. So that allows us to say that the average of the sampling distributions will be the same as the population average, which is 3. That allows us to say that. For the 10% condition, we need a safe assumption, safe to assume $30 is less than 10% of all VA clinics in the States. Which allows us to use this one, which we already figured out on previous page, which worked out to 0.183. Because remember, this was 1 over 30. 1 over root 30, pardon me. And finally, to say that it's normal, well, we're not told the original is normal. In fact, when we looked at it, or when we were shown, it seemed to be skewed to the right. However, the sample size of 30 is greater than or equal to 30. So the large sample condition is met. So that means it's approximately normal, which means we can go ahead and sketch a normal curve. We can label the mean and the standard deviations, and then we can figure out where is 5.33. What's the probability of getting that? Remember, if the probability of getting that is higher than 5%, we use 5% as a guideline, okay? That means it's not that uncommon. It's not that unusual. We just got it by chance. We just happen to get a higher result by chance. So we can't say that the 3-day wait time hasn't been met. However, if it is unusual, if it's a very low probability of happening, okay, then we can say, no, that 3-day wait time is not right. So let's see. So we're going to do our 7 notches. Sketch curve in here. And we're going to start with our mean, which is 3. And then to get the notches to the right, we're going to keep adding 0.183. So 3.183. Cheat here a little bit, 3.366. 3.549. And then we're going to go back to our mean and subtract standard deviations of 0.183. So we're going to get 2.817 for this one, 2.634 for this one, and 2.451 for this. And remember, this represents the sample mean. XR. This is the sampling distribution. It's not the population distribution. So we want to know the probability of getting 5.33 or even higher. Well, hopefully you can see that 5.33 is way to the right of this curve. Like we're going to have to extend this because 3.5. So you figure that's going to be like, the distance is like that for a half. So 4, 4.5, 5, we're way out here. Way out there. Which means we're looking for a really small probability. I mean, that should seem to suggest to us that, oh yeah, that's going to be really small. Okay. But just to confirm, we want to actually find that probability. So this is where we have to use our normal CDF calculation. And remember, we're finding this area here with a lower boundary of 5.33 and a higher boundary of a ridiculously big number. So the lower boundary is going to be 5.33. The upper boundary usually 1,002. The mean, remember, we said it was 3, and the standard deviation, remember, it was 0.183. So thinking that we're probably going to get a really low or small number. And in fact, the number is so small that it can't even be displayed on your screen. It has to be displayed by scientific notation. And it works out to approximately 2.03 times 10 to the negative 27. So imagine, remember scientific notation. If you want an idea of what this looks like, take this decimal and move it 27 places to the left and fill it with zeros. So it's gonna be like 26 zeros and this. That's basically none. That is basically zero. There is a zero probability that we got 5.33 or higher, which obviously is extremely unusual. So the probability of 5.33 days or more occurring is essentially zero. I mean, you can put in that scientific notation number, but basically it's zero. This is extremely unusual. We couldn't have got that by just chance, by sampling variation. I don't know why it's doing this thing. Okay, which suggests it didn't occur by chance. This is extremely unusual, which suggests it didn't occur by chance alone. Therefore, goal of 3 days, we have convincing evidence of that. We have convincing evidence goal of 3 days. That's not being met. So you see how probability comes into play. Okay. So like I said, the next step now is to go the other way. Because the other way is the way problems are normally presented. We don't know about the population. We want to take a sample to make a decent conclusion about the population and to see if claims are true, or to see if something is actually a certain proportion or something is a certain proportion. And that's essentially what we're doing in 7 and 8.